631,000 years ago, the ground beneath what is now Wyoming did something almost impossible to imagine. The Earth opened, not as a single crater, but across a vast section of the landscape, as the ground collapsed into the chamber left behind by an eruption powerful enough to darken skies across an entire continent. It was the last time Yellowstone erupted at full scale, but it was not the first. More than 2 million years ago, an even larger eruption sent roughly 2,400 cubic kilometers, about 590 cubic miles, of volcanic material into the atmosphere. Ash from that event traveled more than 1,900 kilometers, roughly 1,200 miles, before settling across what is now Missouri. The collapsed caldera left behind is enormous. It stretches roughly 48 kilometers by 72 kilometers. That is about 30 by 45 miles. It is so large that from the ground you cannot see where the entire structure begins and ends. And beneath it, the earth is still moving. The ground rises and falls by several centimeters each year, which is a few inches, tracked by instruments and satellites watching Yellowstone continuously. Across the park, thousands of geysers, hot springs, and mud pots release heat and pressure from below. The planet is still breathing here, yet something about the system has changed. The chance of another super eruption in any given year is already extraordinarily small, roughly 1 in 730,000, and recent research suggests even that estimate may overstate the danger. Deep beneath the park, magma is moving, but it may not be moving toward the surface. That is where the story becomes stranger, because scientists have begun finding evidence that the enormous system responsible for Yellowstone's past eruptions may be changing in a way that could eventually make another eruption far less likely. The volcano that once buried enormous parts of North America in ash may not be building toward another explosion. It may be running down, and if that is what is happening beneath Yellowstone, the consequences reach far beyond the next eruption. The evidence is changing how scientists think about where this volcanic system is going and whether its most violent chapter may already be behind it. In this journey, we're going beneath Yellowstone to follow the magma, the ancient eruptions, and the evidence that may reveal what this extraordinary system is becoming. Yellowstone's story begins far below the landscapes visitors can see, where heat rises through solid rock over distances measured in hundreds of miles. The source is a mantle plume, a column of unusually hot material rising from deep within Earth's mantle. It reaches upward from the region near the boundary between the core and mantle, carrying heat through enormous thicknesses of rock as it travels toward the crust. This kind of hotspot behaves differently from a volcano formed where tectonic plates collide or separate. The plume remains relatively fixed while the North American plate moves across it. The continent drifts southwest at about 2.5 centimeters per year, nearly 1 inch, carrying the surface across the heat source beneath it. Each position leaves behind a different volcanic chapter, creating a trail that records the movement of the continent itself. The idea becomes easier to picture when compared with the Hawaiian Islands. There, a stationary mantle plume has produced volcanoes one after another as the Pacific plate travels across it. Yellowstone's system follows a related pattern, except its setting is continental. Instead of oceanic crust, the plume encounters thick continental rock, and that difference changes the chemistry and character of the magma it produces. Yellowstone's hotspot has been active for roughly 16.5 to 17 million years. Its earlier expressions stretch across the Snake River Plain of Idaho, where a chain of volcanic centers extends for about 750 miles. The oldest recognized centers lie near the Oregon Nevada border and date to roughly 17 million years ago. Moving northeast toward Wyoming, the volcanic centers become progressively younger, like pages in a geological record arranged by the motion of the plate. The plume itself reaches more than 1,800 miles into Earth, according to seismic imaging, making it one of the deepest known mantle plumes associated with a volcanic hotspot. That depth matters because the source of Yellowstone's heat is not a shallow pocket trapped beneath the park. It is part of a system connected to processes occurring far inside the planet, where temperatures and pressures are difficult to imagine on a human scale. As the rising heat encounters continental crust, some of that rock melts. The resulting magma becomes rich in silica, producing rhyolite with a thick, resistant character and a capacity to hold substantial amounts of volcanic gas. That combination gives Yellowstone the ingredients for exceptionally explosive eruptions. When enough melt accumulates and becomes mobile, the word hotspot can make this process sound fixed in place and simple, yet the geology is more layered. Heat from the plume does not rise as a single pipe of liquid rock. It spreads, melts portions of the surrounding crust, and feeds different reservoirs at different depths. The chemistry of that crust becomes part of the volcanic story, giving Yellowstone its distinctive rhyolitic character. The surface expression changes as the plate moves, while the deep source continues supplying heat from below. The engine, therefore, has several moving parts, even though its deepest source changes with extraordinary patience. A plume brings heat upward. The continent carries the crust across it. Rock melts, magma evolves, and volcanic centers appear along the path. What looks like one volcano on a map is actually the latest expression of a process that has been tracing the movement of North America for millions of years. The history of Yellowstone can be traced through three enormous breaks in the ground, separated by stretches of time so long that each eruption belongs to a different world. Together, they form the clearest record of how much energy this volcanic system has released during its recent geological history. The first came about 2.1 million years ago in an event known as the Huckleberry Ridge eruption. Roughly 2,400 cubic kilometers, about 590 cubic miles, of volcanic material escaped from the crust. The eruption ranks among the largest individual volcanic events known from Earth's geological record. As the magma chamber emptied, the surface above it lost support and collapsed, leaving a caldera more than 97 kilometers, which is about 60 miles across. Ash traveled far beyond the collapsing landscape. Deposits from the eruption have been identified more than 1,900 kilometers, that is nearly 1,200 miles, away, including locations in what is now Missouri. The volume was thousands of times greater than the material released by the 1980 eruption of Mount St. Helens, placing the Huckleberry Ridge event in a category almost impossible to compare with ordinary volcanic eruptions. About 800,000 years later, Yellowstone's volcanic system produced the Mesa Falls eruption. This event occurred around 1.3 million years ago and formed the Henry's Fork caldera in what is now Idaho. Its output was smaller, approximately 280 cubic kilometers, about 67 cubic miles, yet that quantity still dwarfed the volume of the 1980 Mount St. Helens eruption. The landscape was reshaped across an area that now appears peaceful, its volcanic history preserved mostly in layers of rock. Then came the Lava Creek eruption, about 631,000 years ago. This was the event that formed the Yellowstone caldera recognized today. The collapsed structure covers roughly 77 kilometers from one side to another, which is about 48 miles, and about 116 kilometers across its longer dimension, which is about 72 miles. Evidence also indicates that the main eruption was preceded by smaller volcanic activity near the Sour Creek Dome region, showing that such an event could unfold through a sequence of changes rather than one instantaneous moment. The mechanics begin deep within the crust. Pressure and heat accumulate as magma rises and expands. Fractures develop around the margins of the reservoir, while the surface above can swell. Gas rich magma then moves upward and expands rapidly as pressure falls. When the reservoir loses enough material, the rock above it can no longer remain supported. It collapses inward, creating the broad depression known as a caldera. Around the eruption, pyroclastic currents would have swept outward as mixtures of scorching gas, ash, and broken rock. Their speeds could exceed 160 kilometers per hour, which is about 100 miles per hour. Above them, the eruption column could have climbed roughly 48 to 80 kilometers, that is nearly 30 to 50 miles, into the stratosphere, where enormous quantities of ash and volcanic gases could spread across continental distances. These three eruptions form a geological sequence written directly into Yellowstone's rocks. Their deposits preserve the scale, timing, and reach of the system's most powerful episodes, giving scientists a record of what this landscape has already been capable of producing. After the Great Collapse, Yellowstone did something unexpected. The volcanic system continued to produce lava, yet the character of its activity had changed. Instead of another enormous outpouring of ash and pumice, molten rhyolite began spreading across parts of the new caldera floor in thick flows. These eruptions were smaller in reach, but they still carried enough heat and rock to reshape the landscape. Across the hundreds of thousands of years that followed the Lava Creek eruption, roughly 80 rhyolite lava flows formed within the caldera. Rhyolite is rich in silica, so it tends to move sluggishly compared with basalt. A flow can advance across the ground as a heavy, incandescent mass, gradually cooling from its surface inward. Some accumulated into broad sheets, while others filled depressions left by earlier volcanic activity. The youngest known lava flow dates to about 70,000 years ago. That age gives the geological record an important boundary. Yellowstone has remained thermally active ever since, with abundant hot springs and geysers, yet no confirmed eruption has occurred during that span. The distinction matters because the park's surface can remain intensely heated while the deeper magma system passes through long intervals without producing new lava. Much of this history is preserved as rock rather than written language. Along trails and exposed cliffs, younger rhyolite appears in distinct layers and flow units. Near the Upper Geyser Basin, close to the landscape surrounding Old Faithful, these volcanic rocks form part of the ground beneath modern visitors. Each layer represents a period when molten material reached the surface, spread outward, and eventually hardened into stone. The caldera also contains two broad resurgent domes, Sour Creek Dome and Mallard Lake Dome. These features rose as portions of the crust responded to heat and magmatic processes after the enormous collapse. Their elevation changes are monitored because the domes provide clues about movement within the volcanic system. They are reminders that post eruption landscapes can continue adjusting long after the main event has passed. During the Pleistocene, the volcanic landscape also encountered repeated advances of continental ice. Glaciers moved across the region, carving valleys and altering slopes, while heat from below continued to circulate through fractures and groundwater. Where ice, meltwater, and volcanic heat interacted, unusual geological features emerged. The present landscape, therefore, records two powerful Earth processes occupying the same place, one driven by deep heat and the other by moving ice, each leaving a different signature in the terrain. The timing of Yellowstone's younger eruptions reveals another gradual change. The major caldera forming events became separated by long intervals, while later activity consisted largely of smaller lava eruptions. Eventually, even those became less frequent. 70,000 years have now passed since the last known lava reached the surface, creating the longest documented interval without an eruption of any kind in the modern Yellowstone volcanic record known to scientists today. That span does not mean the volcanic system has stopped functioning. Heat still circulates through rock and water, sustaining the hydrothermal landscape above. Yet the rocks preserve a history in which eruptive activity became progressively less frequent after the last caldera forming event. Layer by layer, the record describes a system whose volcanic output has diminished, leaving behind a landscape shaped by what it once released and by the long interval that followed. For many years, the picture of Yellowstone below the surface had a missing layer. Seismic studies had revealed a shallow reservoir, but deeper rock remained difficult to resolve. Then, in 2015, researchers from the University of Utah identified another reservoir farther down, changing the picture from one chamber into a stacked system with distinct roles. The upper reservoir lies roughly 5 to 16 kilometers below the surface, which is about 3 to 10 miles. Farther down, the lower reservoir extends from about 19 to 45 kilometers, that is nearly 12 to 28 miles, beneath the first. Its size is especially striking. Estimates indicate that the deeper body is more than 4 times larger than the shallower reservoir. If the upper chamber could hold the equivalent of the Grand Canyon 2.5 times, the deeper one could contain enough material to fill it more than 11 times. These reservoirs are not two underground lakes of molten rock. Much of their volume consists of crystallized material, with melt occupying spaces between crystals. Their shapes are inferred from how seismic waves travel through the crust, revealing regions where temperature, composition, and partial melting alter the speed and character of those waves. The resulting picture is closer to a layered network of hot rock and melt than a pair of simple cavities. The chemistry also changes with depth. The upper reservoir is dominated by rhyolitic magma, rich in silica and capable of becoming viscous as it cools and crystallizes. Deeper down, basaltic magma is more fluid and carries heat upward from the mantle. Basalt is familiar from places such as Hawaii, where runny lava can travel across the surface in broad streams. At Yellowstone, much of that basalt remains underground, transferring heat into the crust around it. That heat exchange gives the two reservoirs an ongoing relationship. Basalt entering the lower crust can warm surrounding rock and increase the amount of melt available in nearby regions. Some of that heat can reach rhyolitic magma above, potentially changing its temperature, crystal content, and ability to move. Such transfers are important because rhyolite becomes easier to mobilize as its melt fraction rises. The connection between the reservoirs therefore matters as much as their individual sizes. Magma can move through fractures and narrow pathways, allowing heat and material to pass between different parts of the crustal system. These pathways can open and close as pressure, crystallization, and deformation change. A large volume of magma at depth does not automatically translate into an eruption at the surface. The scale is difficult to picture from above. The park covers a landscape where forests, rivers, wildlife, and roads occupy only a thin surface layer compared with the enormous geological structure below. The magma system extends through many kilometers of crust, which is several miles thick, linking processes occurring at different depths into one connected environment. What appears at the surface as a collection of geysers and hot springs is therefore the upper expression of a much larger architecture. Heat arrives from below, basalt occupies deeper levels, rhyolitic magma resides higher in the crust, and pathways connect portions of the system. The arrangement is immense, intricate, and constantly changing, yet its existence alone does not mean that all of its magma is capable of reaching the surface. The picture of Yellowstone beneath the surface changed when scientists gained a new way to read the electrical properties of the crust. For decades, seismic waves had provided the main clues. Earthquakes send waves through the ground, and those waves travel differently through solid rock, molten material, and fluids. By measuring their paths and speeds, researchers could build an outline of structures that could never be seen directly. A different kind of signal added another layer of detail. Magnetotellurics uses natural electromagnetic fields generated by lightning and activity from the sunday. These fields pass through the crust, where their behavior changes according to the materials they encounter. Magma, water, and solid rock each conduct electricity differently, leaving distinct signatures that instruments can measure at the surface. During 2024 and 2025, researchers applied this method across Yellowstone at an unprecedented scale. The approach offered a new view of the volcanic plumbing, allowing scientists to trace electrical variations through regions that seismic imaging alone could not distinguish as clearly. One researcher compared the improvement to looking through a better camera lens. Structures that had once appeared blended together began to separate into recognizable pieces. The detailed map produced from the 2024 study published in Nature showed that Yellowstone's magma is distributed through a collection of distinct bodies rather than one continuous reservoir. These pockets are linked by narrow pathways, creating a complicated network within the crust. Some regions contain more melt, while others are dominated by crystals and solidified material. The underground system, therefore, has a patchwork character, with different parts existing in different physical states. That arrangement changes how pressure can behave. A single connected reservoir could transmit pressure across a large volume of magma, allowing changes in one region to influence another. Separate pockets have less ability to act as one body. Their narrow connections can restrict the movement of molten material and gases, dividing the system into compartments. The architecture itself becomes part of the reason Yellowstone does not behave like a single underground chamber waiting to release everything at once. Another study, published in 2023, used high-resolution seismic techniques to examine the upper reservoir more closely. The researchers estimated that roughly 28% of the reservoir consists of melt. Earlier estimates had placed the figure between 16 and 20%. The newer measurement was higher, yet it remained below the melt fraction generally associated with an eruption-ready magma body. The distinction is important because imaging does more than reveal where magma exists. It helps scientists determine how much of that material is actually molten, where crystals dominate, and how separate regions connect. A reservoir can contain enormous quantities of hot material while still lacking the mobility required for an eruption. Michael Poland, a geophysicist with the United States Geological Survey, described the newer imaging approach as revolutionary for the detail and resolution it provides. For Yellowstone, that detail turns an indistinct underground structure into something closer to a geological map, where boundaries, pathways, and isolated regions can be traced with increasing precision. The deeper view does not make Yellowstone more dramatic. It makes the system more understandable. What once looked like one immense body of magma is increasingly revealed as a complicated arrangement of separate parts, each responding to heat, pressure, crystals, and fluids in its own way. A closer look at the material inside Yellowstone changes the picture again. Magma is often imagined as a glowing underground lake, its surface hidden beneath miles of rock. In reality, much of a magma reservoir is made of crystals and solid fragments suspended within a smaller amount of liquid. The mixture is called magmatic mush, with a texture closer to wet concrete than a pool of molten stone. That distinction comes from the way magma changes as it cools. Crystals begin forming within the liquid, gradually locking portions of the material into a rigid framework. Melt remains between those crystals, along with gases and other volatile substances. When enough crystals accumulate, the material loses the ability to flow as one mobile body. Heat may still be present, yet mobility becomes increasingly difficult. Researchers use melt fraction to describe how much of a magma system is actually liquid. Studies of erupting volcanic systems suggest that an eruption generally becomes possible when the melt fraction rises into a range of roughly 35 to 50%. Below that range, the crystal framework can keep the mixture too stiff for large-scale movement. The threshold varies between systems, yet the principle helps explain Yellowstone's present condition. Estimates for the upper reservoir place its melt fraction at about 28%. More than two-thirds of its material is therefore crystalline or solid. The reservoir can contain enormous amounts of hot rock and still lack the liquid pathways needed for an eruption. Its physical state matters just as much. Michael Poland of the United States Geological Survey has described Yellowstone's material as mush, emphasizing the mixture of solid rock, crystals, gases, and semi-liquid material. That description changes the mental image completely. Instead of a chamber filled with freely moving molten rock, the reservoir resembles a crystalline framework with liquid threaded through it. Movement requires enough melt to connect those spaces and allow the material to reorganize. The deeper picture is even more restrained. Lower rhyolitic regions, identified in newer mapping, contain melt fractions that are smaller still. The researchers characterize these areas as not presently eruptible. Their material can remain hot and chemically active while being physically incapable of gathering into a mobile body. Heat alone does not guarantee an eruption. This state may also represent a normal part of Yellowstone's long life. A volcanic system can spend substantial periods with relatively elevated melt fractions without crossing into an eruptive phase. Crystals continue forming, heat moves through surrounding rock, and small amounts of melt can remain distributed through the solid framework. The system can persist in this condition for long geological intervals. At the surface, the energy has other pathways. Heat passes into groundwater, warms rocks, drives chemical reactions, and sustains the hydrothermal circulation that characterizes Yellowstone. Some energy leaves through steam and hot water, while other portions remain stored in heated rock. The underground system therefore has time to cool and crystallize even while heat continues arriving from greater depths. Seen this way, Yellowstone's magma is a changing mixture whose ability to move depends on its internal proportions. The amount of liquid, the arrangement of crystals, the pathways between pockets, and the transfer of heat all matter together. The state of the mush is central to understanding why immense quantities of magma can exist without producing an eruption. In the uppermost part of Yellowstone's volcanic system, researchers found a feature that changes how pressure may travel through the crust. In 2025, a team used a Vibrosis truck weighing about 24,000 kilograms, which is about 53,000 pounds, to send controlled vibrations into the ground. The measurements revealed a previously unknown cap above the magma reservoir, positioned roughly 4.2 kilometers below the caldera, which is about 2.6 miles. The cap has an unusual physical character. Its rock contains connected spaces between mineral grains, giving it an estimated total porosity of about 14%. Rather than forming an impermeable barrier, the material allows fluids and volcanic gases to move through narrow cracks and channels. Those pathways create a route by which pressure can migrate upward into the hydrothermal system. Among the gases involved is carbon dioxide, carried upward from deeper magmatic regions, along with other volcanic gases. As these substances move through fractured rock, they can enter water circulating through the crust and eventually reach the surface. The process links the deep volcanic system with the springs, steam vents, and other thermal features scattered across Yellowstone. Brandon Schmant, one of the researchers involved in the study, described the arrangement as an efficient system for venting gas through cracks and channels between mineral crystals. That observation fits naturally with the abundance of hydrothermal activity at the surface. The gases have pathways available to them, and the rock above the reservoir is porous enough to let those pathways remain active. This matters because pressure behaves differently in a system with many outlets. Gas trapped beneath an impermeable layer can accumulate, increasing pressure within the underlying material. A porous cap provides opportunities for gas to escape before that pressure becomes concentrated in one location. The effect resembles a breathable membrane spread across the top of the reservoir, allowing movement through many tiny passages. The discovery also gives another perspective on Yellowstone's familiar surface activity. Steam rising from vents, water surging through geysers, and gases emerging from fumaroles are connected to the circulation of heat and fluids through the crust. Their presence reflects an active hydrothermal system with numerous routes toward the surface. The energy beneath the caldera, therefore, has many ways to leave the deeper rock. Researchers describe the volcanic system as being in a state of repose, a term that means the system remains active while experiencing a period without eruption. The distinction is important. Repose does not mean the heat source has disappeared, and it does not mean the hydrothermal system has stopped functioning. It describes a volcanic system whose present conditions do not favor an eruptive event. The porous cap adds a physical explanation for part of that state. Instead of sealing the upper reservoir beneath a rigid barrier, the rock permits gases to travel through its mineral framework. Heat and fluids continue circulating, while some pressure is released along the way. Yellowstone remains a living geological system, yet the structure above its magma provides space for that system to breathe, with pressure finding many small pathways through the crust. The cap sits close to the top of the magma system, where permeability can influence how fluids move. Its internal structure connects the reservoir with the hydrothermal network above. The crust can distribute gases through many microscopic routes, with each carrying only a small portion of the total flow. Beneath the familiar landscape, Yellowstone is constantly adjusting its shape. Instruments positioned across the caldera record the ground rising and falling as underground fluids move through fractures and as magma shifts at depth. Satellite measurements can detect changes of only a few centimeters, yet over broad areas, those movements become part of a long geological rhythm. The surface responds to processes occurring far below, even when nothing dramatic is visible above. During one 7-year period, researchers measured uplift reaching as much as 10 inches, or about 25 centimeters, in some locations. The scale and extent of that movement were extraordinary, yet uplift alone does not indicate that an eruption is approaching. Yellowstone has experienced repeated phases of rising ground, followed by subsidence, when the surface settles again. Such cycles can reflect changes in water, steam, and molten rock moving through the crust. The earthquakes provide another expression of this restless system. Yellowstone is the most seismically active region in North America, with roughly 1,500 to 2,500 located earthquakes in a typical year. During 2024, monitoring recorded 1,173 below that usual range. Earthquakes at Yellowstone are generally small, and many are detected only by instruments, forming a continuous record of fractures shifting through the crust. One event stands apart from that background. On March 30th, 2014, an earthquake with a magnitude of 4.8 occurred near Norris Geyser Basin. The shaking was felt across portions of Montana and Wyoming, while the underground fractures continued to rearrange themselves afterward. Events like this can modify pathways through which heated water and steam travel, creating temporary changes in the underground circulation network. That connection between earthquakes and hydrothermal activity is especially important. Yellowstone's geysers and hot springs depend on an intricate network of cracks and conduits underground. Water descends through fractures, encounters heat, and rises again through channels shaped by pressure and mineral deposits. Small earthquakes can reopen or redirect some of those pathways, helping maintain the circulation that feeds surface features. Old Faithful, for example, depends on a deep plumbing network that allows water to move, heat, and pressure to interact beneath the geyser. The relationship is indirect and complex, but seismic activity can help preserve the fractures needed for hydrothermal circulation. In this sense, some of the shaking that seems disruptive at the surface participates in maintaining the pathways that make Yellowstone's geysers possible. Ground deformation follows a similarly fluid pattern. When pressure or fluids accumulate beneath part of the caldera, the surface may rise. When those fluids migrate away or pressure decreases, the ground can settle. Magma movement can also contribute to these changes. The important feature is the alternation itself. A system that repeatedly rises and subsides is behaving dynamically, with material and energy being redistributed through the crust. Seen together, the earthquakes and changing elevation form a living record of Yellowstone's interior. The caldera does not remain fixed while the volcanic system beneath it works. It bends, shifts, and settles as water, gases, heat, and magma move through an interconnected geological structure. Each small adjustment becomes another measurement of that movement, preserving a record of a volcano that remains active without showing the pattern expected from a system steadily building toward catastrophe. The surface of Yellowstone carries thousands of openings where heat, water, and gases find their way upward. More than 10,000 hydrothermal features are scattered across the park, including geysers, hot springs, fumaroles, and mud pots. Together, they form the greatest concentration of active hydrothermal features on Earth, with nearly half of the world's geysers gathered within one landscape. Their presence offers a glimpse into how energy moves through the crust without requiring a volcanic eruption. A geyser begins with ordinary groundwater. Rain and melting snow seep downward through fractures, descending into a network of rock warmed by the volcanic system. As the water approaches heated depths, pressure keeps it from boiling immediately. More water enters from above, increasing the weight of the column, while dissolved gases and steam collect within the plumbing. Eventually, pressure changes allow a portion of that water to flash into steam, expanding rapidly and pushing the remaining water toward the surface. Old Faithful depends on a particularly shaped underground conduit. A narrow section acts as a natural throttle, allowing pressure and heat to accumulate before the eruption begins. Once the balance shifts, heated water and expanding steam surge upward in a column. The structure of the plumbing gives the geyser its characteristic behavior, turning underground circulation into a repeating surface event. Grand Prismatic Spring reveals another side of this system. The pool measures about 113 meters, which is about 370 feet, across and reaches roughly 37 meters, that is nearly 121 feet, in depth. Its striking bands of color come largely from communities of heat-adapted microorganisms. Different organisms flourish at different temperatures, creating changing zones of yellow, orange, green, and blue around the water. At Norris Geyser Basin, Steamboat Geyser can send water roughly 91 to 122 meters, which is about 300 to 400 feet, into the air. That makes it the tallest active geyser known on Earth. Old Faithful usually reaches only about 30 to 55 meters, that is nearly 100 to 180 feet, during its eruptions. Each geyser expresses the same basic relationship between heat, water, pressure, and the shape of its underground channels. Mud pots follow a different path. Acidic water interacts with volcanic gases and surrounding rock, breaking the rock down into fine clay. Bubbles rise through this slurry, making the surface heave and churn like a slow geological process unfolding in plain sight. Fumaroles carry the process further by releasing steam and gases through openings where little or no liquid water reaches the surface. Among those gases are carbon dioxide, hydrogen sulfide, and sulfur dioxide, substances that also occur in volcanic systems during eruptions. These features do not function as a simple safety valve that guarantees an eruption cannot occur. Their importance lies in showing that heat, water, and gases have numerous pathways through the crust. Energy can move upward through thousands of separate channels instead of remaining concentrated in one place. The hydrothermal landscape is therefore part of Yellowstone's circulation system, transforming deep volcanic heat into springs, steam, mud, and erupting water at the surface. For tens of thousands of years, that circulation has remained one of the clearest expressions of a volcanic system releasing energy through many ordinary openings. The number often attached to Yellowstone is 1 in 730,000, an annual estimate for a caldera-forming eruption. It sounds precise, almost as though the volcano has been assigned a schedule. In reality, the figure is a rough statistical average drawn from only two intervals between three enormous eruptions. The United States Geological Survey itself emphasizes that such a calculation is not a prediction and that another catastrophic eruption may never occur. Placed against the scale of a human lifetime, the number becomes almost difficult to picture. A single year carries roughly one chance in 730,000 of a caldera-forming event based on that historical average. The probability is extraordinarily small, while smaller volcanic events remain more plausible. Even the annual figure should be held with some caution because it comes from an extremely small historical sample. It is useful for perspective, though it cannot tell us what Yellowstone will do in any particular year. Yellowstone's volcanic system contains many possible pathways for future activity, from lava flows to hydrothermal explosions, and a future eruption would not automatically resemble the three enormous events preserved in its past. The comparison with major asteroid impacts provides another sense of scale. Estimates for civilization threatening asteroid impacts fall within a similarly rare range. roughly one chance in 500,000 to one chance in 1 million during a given year. These numbers describe different hazards and come from different methods, so they should never be treated as interchangeable forecasts. They do, however, place Yellowstone's calculated annual probability among the rarest natural events considered in long-term hazard assessment. The idea that Yellowstone is overdue comes from a misleading shortcut. The three major eruptions occurred about 2,080,000, 1,300,000, and 631,000 years ago. The gaps between them were approximately 780,000 years and 670,000 years. Those intervals are different from one another, and two intervals are far too few to establish a repeating timetable. Volcanoes respond to changing conditions inside the crust, including magma supply, crystallization, pressure, and the movement of fluids. There is no geological clock counting toward a predetermined date. The passage of time can even work against the simple overdue story. As magma cools, crystals grow within it, reducing the amount of liquid material available to move and erupt. Heat is transferred into surrounding rock, while fluids migrate through fractures and hydrothermal pathways. A long interval can therefore represent continued cooling and crystallization rather than the accumulation of an inevitable eruption. Recent monitoring adds another piece to that picture. During 2024, scientists located 1,173 earthquakes in the Yellowstone region, below the usual yearly range of roughly 1,500 to 2,500. The volcano alert level remained normal, and measurements showed background levels of seismicity, deformation, and thermal activity. The caldera continued to subside by a few centimeters each year, so the famous probability is best understood as a historical calculation, not a countdown. Current observations do not show Yellowstone moving toward a supereruption, and the available evidence gives scientists no reason to treat the volcano as overdue. The number remains small, while the physical system beneath it continues to evolve through cooling, crystallization, fluid movement, and the ordinary adjustments of a living volcanic landscape. Far below the forests and steaming ground of Yellowstone, the source of its heat reaches toward the deepest parts of Earth. Seismic images suggest a mantle plume extending nearly 2,900 kilometers, which is about 1,800 miles, into the planet, reaching toward the boundary between the mantle and the core. This immense column of hot material is less like a moving river and more like a persistent thermal presence, rising through solid rock over geological time. Its position has changed little at depth, while the North American plate has traveled southwest above it. The difference is subtle on any human timescale. The plate moves only a few centimeters each year, yet across 16.5 million years, that motion has carried the surface far enough to leave a trail of volcanic centers, stretching from the region of Nevada and Oregon toward Yellowstone. Each center marks a former meeting place between the plume's heat and the crust above it. That history reveals something important about the system's future. The plume itself can remain steady while the volcanic landscape above it changes. As the plate continues its journey, the hot material encounters crust with different thicknesses, compositions, and temperatures. Those differences influence how much rock can melt, where magma gathers, and how long that magma remains capable of moving. The change can already be read in the western portions of Yellowstone's volcanic system. Some rhyolitic magma there represents remnants of older activity and has continued to cool and crystallize. As crystals occupy more of the magma, the remaining melt becomes less abundant and less able to move through the surrounding rock. The chambers gradually become more like solidified records of an earlier thermal phase. Farther toward the northeast, The relationship between the deep heat source and the crust takes another form. The volcanic track itself records this migration of activity. Older volcanic centers lie southwest, while progressively younger centers appear toward Yellowstone. The sequence is a geological trail left by a moving continent crossing a relatively fixed source of heat. The plume has remained persistent, while the surface has carried new crust into its influence. There is a deeper rhythm here. Heat rising from the mantle does not guarantee an eruption at the surface. It must pass through layers of rock that can absorb, redirect, or resist that energy. Some heat becomes magma, some warms groundwater and feeds hydrothermal circulation. Some is stored within rock before gradually escaping. The same deep source can therefore produce very different surface expressions as the crust changes. For roughly 17 million years, this interaction has shifted northeastward along the continent. The older volcanic fields mark places where the plume once had a stronger connection with the surface. Yellowstone represents the youngest major expression of that long progression. Its present activity is therefore part of a moving geological story rather than a permanent arrangement fixed beneath one location. The plume continues to supply heat, but the crust above it is changing the terms of that exchange in ways that unfold across immense spans of geological time. Cooling western chambers, crystallizing magma, and the progressive movement of volcanic centers all point toward a system whose surface expression can weaken as the plate carries new terrain across the deep source. The heat remains, yet its ability to create large volumes of eruptible magma depends on what lies above it. The map of Yellowstone's deepest workings now carries a subtle direction, a tendency that points away from the western caldera and toward the northeast. Recent magnetotelluric imaging has traced the strongest concentration of rhyolitic melt storage into this northeastern region, where it meets a lower crustal source of basaltic heat. The pattern suggests that the center of future volcanic activity, if it ever develops again, has shifted across the caldera. That shift is measured across geological time, with no implication of an approaching eruption or a rapid change at the surface. For roughly 160,000 years, much of the post-caldera volcanic activity has been concentrated farther west. That history is written into the older lava and magma bodies scattered through the western portion of the system. Those reservoirs are now losing heat and crystallizing. Their former importance makes the present migration especially interesting. The volcanic system has changed its preferred location while the deeper source remains persistent, tracing a gradual change through the crust over immense ages. The northeastern reservoirs occupy a different setting. Here, rhyolitic melt is linked more directly with heat rising from the lower crust. That connection gives this part of Yellowstone the greatest concentration of stored rhyolitic melt identified in the recent imaging. It does not mean an eruption is approaching. It means that, among the remaining magma reservoirs, this region has the geological ingredients most closely associated with future rhyolitic volcanism. Beyond the caldera, however, the landscape changes dramatically. The northeast path leads toward the Beartooth Plateau, a region underlain by some of the thickest and oldest continental crust in North America. This rock has endured for immense spans of geological time. Its thickness and strength create a difficult barrier for heat rising from below. A plume can deliver thermal energy for millions of years, yet turning that energy into large quantities of eruptible magma requires the surrounding crust to cooperate. The North American plate continues its gradual southwest movement, carrying the surface across the stationary plume. That motion means the relationship between deep heat and shallow rock is continually being rearranged. A source that once encountered crust, capable of melting relatively easily, can eventually find itself beneath rock that absorbs the heat without producing much magma. In that sense, the direction of Yellowstone's volcanic history may contain the seeds of its eventual decline. Scientists cannot yet say exactly what will happen when the plume becomes more deeply associated with the Beartooth Plateau. Thick crust may suppress melting so effectively that major volcanism fades away. Another possibility remains that enough heat could accumulate to produce new magma through processes that are not yet fully understood. Geological systems rarely offer certainty at such enormous scales. What can be seen today is more restrained. The western reservoirs are cooling, while the northeastern reservoirs hold the greatest remaining concentration of rhyolitic melt. The plume continues to rise from the deep mantle, and the continent continues to move above it. Their meeting point is therefore changing, almost imperceptibly, across millions of years. Michael Polland has described the long-term possibility in equally broad terms. Another eruption could occur on million-year timescales, or Yellowstone might never erupt again. Both possibilities fit within the slow arithmetic of a planet where landscapes can spend millions of years becoming something entirely different. Yellowstone's great eruptions do not form a simple countdown toward extinction. The first, around 2.1 million years ago, released about 2,450 cubic kilometers of material, which is about 590 cubic miles. The second, around 1.3 million years ago, was far smaller, producing about 280 cubic kilometers, or nearly 67 cubic miles. The third, about 631,000 years ago, grew larger again, releasing roughly 1,000 cubic kilometers, or about 240 cubic miles. The sequence is not a steady decline in size. The character of the system, however, has changed since those immense events. After the latest caldera-forming eruption, Yellowstone entered a different phase. Around 80 mostly non-explosive eruptions have been identified since then, including rhyolitic lava flows and basaltic vents. Many were small compared with the eruptions that created the calderas. The youngest known lava flow erupted about 70,000 years ago. Since that time, heat and hydrothermal activity have remained, while no new lava has reached the surface. That interval becomes more meaningful when paired with the condition of the magma underground. The upper reservoirs contain abundant crystals. Their melt is divided among separate pockets, and several western bodies are cooling. None of this proves that Yellowstone has reached the end of its volcanic life. It does describe a system whose magma is becoming less connected and less able to move as one body. The older volcanic fields along the Yellowstone hotspot track offer another clue. The trail extends roughly 1,200 kilometers, which is about 750 miles, across the Snake River Plain. It contains older caldera systems formed as the North American plate moved across the mantle plume. Those centers eventually cooled, their shallow magma systems solidified, and their volcanic landscapes became geological records. Henry's Fork caldera provides a nearby example. Its major eruption occurred around 1.3 million years ago, followed by later volcanic activity before the center shifted toward the modern Yellowstone region. The older system shows how a hotspot can remain thermally active while individual volcanic centers fade. Activity can migrate, diminish, and eventually cease at one location. Yellowstone may be following part of that pattern. The plume remains active, magma still exists, and heat continues circulating through the crust. Those facts prevent scientists from declaring the system extinct. At the same time, cooling reservoirs, fragmented melt storage, and a long absence of lava describe a configuration far removed from the conditions that produced the great caldera-forming eruptions. There is no geological clock waiting for another event. The record shows a volcanic system capable of changing over hundreds of thousands or millions of years. Another large eruption remains possible, while another future is also plausible, one in which remaining magma gradually crystallizes and the volcanic center loses its ability to produce major eruptions. If Yellowstone is approaching a threshold, it would be a gradual transition rather than a single moment. Heat could remain long after large eruptions became impossible, and hydrothermal activity could persist after deeper volcanic machinery weakened. The end of the caldera forming era would therefore arrive as geological fading, measured in cooling rock, diminishing melt, and the slow transformation of an active volcanic center into a record of what Earth once did there. A supereruption belongs to a scale that is difficult to hold in the imagination because human history contains no direct comparison. Yellowstone has produced 3 eruptions classified at the highest level of the Volcanic Explosivity Index. This level represents events releasing more than 1,000 cubic kilometers, which is about 240 cubic miles of volcanic material. The first Yellowstone eruption released roughly 2,450 cubic kilometers, which is about 590 cubic miles. By comparison, the 1980 eruption of Mount St. Helens released less than 1 cubic kilometer, or less than 1/4 of a cubic mile, and belonged to a much lower category. The difference is more than a matter of size. A great Yellowstone eruption would send an enormous column of ash and gas upward through the atmosphere, potentially reaching 50 to 80 kilometers, which is about 30 to 50 miles, into the stratosphere. At that height, the eruption would interact with powerful atmospheric currents while generating turbulent winds around the rising column. Ash would spread across enormous distances, carried far from the source. The surrounding states would bear the heaviest burden. Wyoming, Montana, and Idaho could receive ash measured in meters, with some areas potentially accumulating several meters, which is about several feet. Wet volcanic ash is unusually heavy, and even a much thinner layer can place severe loads on roofs, machinery, roads, and other infrastructure. Transportation would become difficult as roads and airports were covered, while visibility and engine performance deteriorated. The disruption would extend far beyond the ashfall zone. Air travel across much of the United States and Canada could be interrupted because fine ash is dangerous to aircraft engines. Electrical infrastructure could also be damaged when ash becomes wet and conductive, creating pathways for electrical current across equipment. Water treatment, communications, fuel distribution, and food supply networks would face connected pressures as transportation and power systems became less reliable. The effects on agriculture could be especially broad. Thick ash can bury crops, damage machinery, alter soils, and reduce the sunlight reaching plants. Major agricultural regions across Iowa, Illinois, Kansas, and Nebraska would lie within the wider zone of concern. Rivers and reservoirs receiving ash and volcanic material could also experience contamination, particularly where metals and other chemicals entered the water. The Missouri River begins in the broader Yellowstone region, and material deposited across its watershed could eventually move downstream through the Missouri and Mississippi River systems. Arsenic and other elements associated with volcanic ash can become environmental concerns when released into water and soil. The consequences would therefore extend through connected landscapes rather than stopping at the eruption itself. Evidence of Yellowstone's earlier reach already rests across the continent. Ash layers from past eruptions have been identified far from the caldera, preserved in soils and sediments from the western United States toward the Mississippi Valley. Those layers are geological reminders of how widely a single eruption can distribute material. Understanding that scale gives meaning to the possibility that Yellowstone may never produce another event of this magnitude. The absence of another supereruption would leave a world spared from an upheaval capable of disrupting atmosphere, agriculture, transportation, water, and power across an immense region. The volcanic system may remain active for a very long time, yet the particular kind of eruption that created its greatest scars could belong to a chapter that is gradually closing. A plume from a truly immense eruption would rise beyond the familiar weather of the lower atmosphere, climbing perhaps 48 to 80 kilometers, which is about 30 to 50 miles, before spreading through the stratosphere. At that height, the behavior of the ash would change. Ordinary volcanic plumes are shaped strongly by prevailing winds, producing long deposits that stretch away from the volcano. A Yellowstone supereruption would generate something different, an umbrella cloud expanding outward from the top of the rising column. The physics begins with the immense quantity of hot material entering the atmosphere at once. As the plume rises and spreads, its umbrella cloud can expand radially, generating winds within the cloud itself. Computer modeling by the United States Geological Survey found that this expansion could drive ash more than 1,500 kilometers, which is about 931 miles, against the surrounding wind field. The atmosphere would still matter, yet the eruption would partly determine its own pattern of movement. That distinction changes the shape of the ashfall. Instead of forming a narrow fan extending downwind, deposits would tend toward a broad bullseye centered on Yellowstone. The heaviest material would remain closer to the source, with thickness decreasing outward across the continent. Modeling suggests that the affected region could extend across more than 2.5 million square kilometers, which is about 1 million square miles, reaching far beyond the Rocky Mountains and into Canada and the central United States. Across that enormous footprint, the ash would arrive in layers rather than as one uniform blanket. Geography, eruption, duration, particle size, and changing winds would all alter the pattern from place to place. Closer to the caldera, accumulation could reach meters, which is about several feet, especially across the northern Rocky Mountains. Wyoming, Montana, and Idaho would lie within the region expected to receive the greatest deposits. Farther away, the layers would become thinner, yet even a few centimeters, which is about an inch or more, could interfere with machinery, agriculture, transportation, and water treatment. Fine volcanic ash is made of tiny fragments of volcanic material that can damage engines and become difficult to remove once it enters infrastructure. The atmosphere would carry another part of the story upward. A plume reaching the stratosphere could deliver sulfur dioxide into a region where atmospheric circulation moves material around the globe. There, chemical reactions can transform sulfur dioxide into sulfate particles that reflect some incoming sunlight. The resulting cooling would depend on the amount injected, the altitude reached, and how efficiently the particles spread. The image that emerges is therefore larger than a column rising above a volcano. The eruption would reshape the movement of its own ash cloud, pushing material outward across directions that ordinary weather would normally separate. Historical Yellowstone deposits already preserve evidence of this unusual dispersal. Ash from enormous eruptions has been identified thousands of kilometers from the caldera, showing that the atmosphere can carry volcanic material across continental distances. For a moment, the sky itself would become part of the eruption's machinery. The plume would rise, spread, and establish an immense atmospheric presence, while the smallest particles entered circulation far beyond the original landscape. What begins above Yellowstone could therefore become a continental and atmospheric event, written across the air as much as across the ground. Ash has a strange physical character. It looks weightless while falling, yet each particle is a fragment of rock or volcanic glass, sharp enough to abrade surfaces and fine enough to enter machinery, lungs, and water systems. Once mixed with moisture, the material becomes dramatically heavier. Across the regions closest to Yellowstone, that difference would turn falling ash into a structural burden measured in meters, which is about 3.3 feet for every meter. Across more than 2.5 million square kilometers, which is about 1 million square miles, the deposits would vary greatly. Within roughly 483 kilometers, that is nearly 300 miles, of the caldera, deposits from a giant eruption could accumulate to substantial depths. Roofs would carry the first burden. A layer of wet ash, only a few centimeters thick, can weigh heavily across a broad surface, and deeper deposits would increase that load continuously. Buildings designed for ordinary snow, rain, and wind would face conditions far beyond their intended limits. The ground itself would become difficult to cross. Roads, railways, and airport runways could disappear under layers of powder and grit. Vehicles would struggle as ash entered engines and moving parts, while visibility and traction deteriorated. Clearing routes would require enormous quantities of labor, equipment, and fuel. Electricity would encounter another problem. Volcanic ash can become electrically conductive when wet, allowing current to travel across surfaces that normally insulate electrical equipment. Substations, transformers, and transmission components could accumulate deposits and fail through short circuits or contamination. A damaged electrical network would affect refrigeration, communications, hospitals, water treatment, fuel distribution, and countless other systems that depend on continuous power. Water infrastructure would face a similar chain of problems. Ash entering reservoirs could alter water quality, while filtration systems could become clogged by fine particles. Surface water would carry suspended material downstream, forcing treatment facilities to process enormous quantities of contamination. Communities depending on rivers, reservoirs, or shallow groundwater would have to manage supplies under difficult conditions. Far above the ground, the smallest ash particles could remain suspended in the atmosphere for weeks. Their presence would reduce incoming sunlight across parts of North America and create a prolonged dimming effect over regions far from the eruption. The particles would also degrade air quality, with the finest fragments capable of penetrating deep into the respiratory system. The disturbance would reach places that received little visible ash as well. Supply chains would depend on roads, railways, aircraft, electricity, and clean water, linking distant communities to the heavily affected interior. A thin coating hundreds or thousands of kilometers away could still interfere with transportation and commerce. Geological layers preserve a record of this scale. Yellowstone ash beds have been identified across distant parts of the continent, including areas near the Gulf Coast and Atlantic seaboard. Those deposits are reminders that an eruption can spread material far beyond its source. The deepest deposits would remain concentrated near the source, while thinner layers spread outward across valleys, plains, farms, towns, and forests, changing the surface beneath them. The ash zone would therefore be measured in more than thickness. It would be measured in the reach of its effects, from buried landscapes near the caldera to disrupted systems far beyond the heaviest deposits. A field of corn can endure drought, insects, and storms, Yet a blanket of volcanic ash would bring a different kind of disruption. Across Iowa, Illinois, Indiana, Kansas, Nebraska, and Minnesota, enormous areas of farmland support corn, soybeans, wheat, and livestock. These fields are part of a food network extending far beyond the farms themselves, carrying grain towards cities, ports, mills, feedlots, and distant countries. Even a shallow layer of ash can overwhelm a growing crop. Fine particles cover leaves and interfere with the exchange of gases and sunlight that plants require. Heavier deposits bend or bury stems, while wet ash can form dense layers across the soil. Where accumulation becomes deeper, fields could lose their normal structure, drainage, and chemistry. Recovery would depend on the depth of the deposit and the condition of the underlying soil, with some farmland potentially remaining difficult to cultivate for years. Livestock would encounter another problem as the same material settled across pasture and water. Volcanic ash contains sharp particles capable of irritating the eyes and respiratory passages of animals. Grazing animals could ingest ash while feeding, while contaminated water sources would add another burden. Dairy and meat production would therefore become harder to maintain at the same moment that crop harvests were failing. Water would connect these separate pressures. The Missouri River begins in the Rocky Mountains west of the Central Plains and eventually joins the Mississippi River. Ash and sediment entering watersheds could carry contaminants downstream, while treatment facilities would have to manage unusually heavy loads of suspended material. Arsenic and other elements can occur in volcanic material, although their actual concentrations and movement would vary with the chemistry of the ash and the receiving environment. Power shortages would deepen the agricultural disruption. Farms depend on electricity and fuel for pumps, refrigeration, grain handling, ventilation, irrigation, communications, and processing. If electrical equipment became coated or damaged by ash, operations could stop even where fields remained physically intact. A farm can have healthy crops and still lose the ability to harvest, store, dry, or transport them. Food reserves would provide some time, yet reserves are measured against ordinary consumption, while a major volcanic disaster would disrupt production and distribution simultaneously. Historical estimates have placed United States food reserves at only a limited number of weeks under normal conditions, with one estimate from the early 21st century suggesting roughly 74 days. Such a figure describes existing stores, not a guaranteed emergency supply, and it would offer little protection against a prolonged interruption of farming and transport. Markets would respond before empty shelves appeared. Grain prices could rise as traders anticipated shortages, while countries dependent on American exports would begin searching for alternative suppliers. The effects would move through shipping routes, livestock feed, food processing, and household costs, turning a geological event into an international economic disturbance. That is why the agricultural consequence reaches beyond the fields themselves. A harvest is part of a chain involving soil, water, electricity, machinery, storage, transportation, markets, and time. Break several links together, and replacing the lost harvest becomes far more difficult. Yellowstone's ash would therefore touch the food system at many points at once, transforming fertile ground into a landscape where recovery would depend on the slow return of clean water, workable soil, functioning infrastructure, and another growing season. The first changes would begin high above the clouds, where an eruption can alter the balance of sunlight reaching the ground. A Yellowstone supereruption would send sulfur dioxide into the stratosphere, a region far above most weather. There, the gas could spread across enormous distances before returning toward the surface. Its journey would become part of a planetary process, linking an eruption in North America with skies over oceans, forests, deserts, and fields on every continent. Within the stratosphere, sulfur dioxide reacts with water vapor and forms sulfate aerosols, tiny droplets containing sulfuric acid. These particles can remain suspended for 1 to 3 years, and some may persist longer. Rather than falling rapidly with ordinary ash, they become part of a high atmospheric veil. Sunlight passing through this layer encounters countless particles that scatters some incoming solar radiation back toward space. Less energy reaches Earth's surface, and the planet begins to cool. Because the stratosphere circles the globe, the influence would gradually extend far beyond the original eruption zone. A glimpse of this process came from Mount Pinatubo in 1991. That eruption was far smaller than a Yellowstone supereruption, yet it released roughly 20 million tons of sulfur dioxide into the stratosphere. Global average temperatures fell by about 1/2 degree Celsius, or about 1 degree Fahrenheit, for roughly 2 years. The change was modest compared with the scale considered possible at Yellowstone, but it demonstrated how a volcanic eruption can influence climate far beyond its immediate surroundings. A larger release could produce several degrees Celsius of cooling, or roughly 5 to 9 degrees Fahrenheit, sustained across multiple years. The exact magnitude would depend on the amount of sulfur dioxide released, the height reached by the eruption column, and the state of the atmosphere at the time. Even a moderate shift in global temperature can reshape the seasons on which agriculture depends. Fields near the edges of suitable growing regions would be especially sensitive. A shorter summer could prevent crops from reaching maturity. Frost could arrive before harvests are ready, while altered rainfall could bring drought to one region and excessive moisture to another. Monsoon systems could shift, changing the seasonal rhythm that supports hundreds of millions of people. Oceans would also respond as the atmosphere cooled, adding another layer to the rearrangement of weather patterns. History offers a distant example. In 535 of the Common Era, a major volcanic eruption, possibly associated with a source in the tropics, was followed by a prolonged period of unusual cooling. Tree growth records, ice evidence, and other climate archives preserve signs of disrupted conditions. Crop failures, famine, and political instability appeared across parts of Europe, Asia, and the Middle East during the difficult years that followed. The exact volcanic source remains debated, yet the climate response demonstrates how atmospheric particles can echo through human societies. A Yellowstone-scale volcanic winter would extend that lesson across a far larger stage. Food production would depend on seasons that had shifted, water cycles that had changed, and sunlight arriving through an atmosphere carrying the remnants of a single immense eruption. The event would begin at one point on Earth, while its climatic consequences would belong to the whole planet across broad regions of the world. A layer of ash in a distant landscape can preserve a moment far older than any written history. One of the clearest examples comes from Toba, a volcanic system on the island of Sumatra in Indonesia. About 74,000 years ago, it produced the largest known volcanic eruption of the past 2.5 million years. The event left a marker that can still be traced across parts of the world, giving geologists a rare view of what a colossal eruption can leave behind. Toba released an estimated 2,800 cubic kilometers of volcanic material, which is about 672 cubic miles. That volume exceeded the material produced by any of Yellowstone's three great caldera-forming eruptions. The eruption belongs to the highest category of the Volcanic Explosivity Index, a scale used to describe the magnitude of explosive eruptions. Its ash traveled far from Sumatra, settling across South Asia, the Indian Ocean, and parts of East Africa. Those deposits became known as the Youngest Toba tuff. In layers of sediment and rock, they form a recognizable horizon that can be compared across enormous distances. Ocean sediments preserve traces of the event. Rock layers carry the same chemical signature. Ice records in distant regions also contain evidence associated with the eruption. The scattered fragments become a kind of planetary archive, allowing scientists to reconstruct an event that unfolded long before written memory. The atmosphere may have carried another consequence. Sulfur released during the eruption could have formed reflective particles high above the surface, reducing incoming sunlight and contributing to a period of global cooling. Toba erupted during an already cold glacial interval, so its climate influence unfolded within a world that was already experiencing major environmental change. Some studies have proposed that the eruption intensified cooling for several years, affecting ecosystems across wide regions. One of the most intriguing parts of the Toba story concerns our own species. Genetic studies have proposed that the human population experienced a severe bottleneck around this period, with the number of surviving humans possibly falling to the tens of thousands. The idea has attracted extensive scientific debate, and other evidence suggests human populations were more resilient and geographically varied than a single catastrophic decline would imply. The genetic record, therefore, remains an active field of study rather than a settled account of Toba's aftermath. The geological evidence requires less interpretation. A supereruption leaves traces that outlive civilizations, climates, and individual landscapes. Its ash can cross oceans, settle into sediments, and become part of rock for tens of thousands of generations. Toba demonstrates that an eruption of this magnitude belongs to Earth's real history, recorded across multiple continents rather than imagined from theory alone. There is also a difference between the world of Toba and the world that exists today. Human communities now depend on networks extending across continents. Food moves through long supply chains, electricity links distant regions, and agriculture relies on carefully timed seasons, transportation, fuel, and water systems. A prolonged atmospheric disruption would therefore pass through many connected layers of modern life. Toba shows that the planet can endure an immense volcanic disturbance. It also leaves a record of how far the consequences can travel, written in ash that remains long after the eruption itself has disappeared. A thin band of pale material can carry the memory of an eruption across an entire continent. In the layers of sediment left behind by Yellowstone, ash becomes more than debris. Each deposit contains a chemical and mineral signature formed from the magma that produced it. Those signatures can be measured, compared, and matched, allowing geologists to connect an isolated patch of ancient ash with the eruption that created it. The Huckleberry Ridge eruption, which occurred about 2.1 million years ago, left one of the broadest traces. Its ash has been identified in sediments and rock formations as far east as Missouri and as far south as Louisiana, more than 1,200 miles from Yellowstone. The material traveled through the atmosphere before settling into lakes, soils, river deposits, and other environments. Once buried, those particles became part of the geological layers surrounding them. Some deposits were later compressed, exposed by erosion, and examined again after landscapes had changed around them. Their survival allows modern researchers to follow a single eruption through places that now seem completely unrelated. These deposits are known as tephra layers. They can appear as narrow bands within much thicker sequences of sediment, sometimes separated from neighboring layers by thousands or millions of years. Their value comes from the distinctive chemistry carried by the volcanic glass and minerals. When a matching signature appears in distant locations, scientists can recognize that the layers formed during the same eruption, even when the landscapes around them have changed completely. That makes Yellowstone ash useful as a geological clock. Paleontologists studying Ice Age deposits across the Great Plains can use recognizable volcanic layers to establish the relative ages of sediments containing fossils, pollen, bones, and other traces of past life. A layer created during a known eruption provides a fixed point within the surrounding sequence, helping scientists place other discoveries into the larger history of the landscape. The thickness of an ash layer adds another dimension. A heavier deposit generally records greater accumulation at that location, while thinner deposits mark places farther from the main ashfall zone. By comparing these layers across many sites, geologists can reconstruct the shape of the ancient deposit and estimate how widely the eruption affected the surrounding region. Variations in grain size and thickness can also reveal how particles were carried through the atmosphere before reaching the ground. A canyon wall in Kansas can therefore preserve information about an eruption that occurred far to the west. The ash within its layers can help establish the reach of the eruption plume, the distribution of falling material, and the relationship between different deposits. What looks like a narrow stripe in stone becomes part of a much larger map when it is compared with matching layers elsewhere. Yellowstone's record is unusually valuable because its major eruptions produced ash that traveled across enormous areas while retaining distinctive chemical characteristics. The farther those layers can be traced, the more complete the picture becomes. Rock preserves the event in fragments, and each fragment adds another point to the reconstruction. Through those layers, the past eruptions of Yellowstone remain measurable across landscapes that have since changed, carrying their chronology forward long after the original ash settled. The stone therefore becomes a record with its own sequence, preserving distance, timing, composition, and scale within a single physical archive. Around Yellowstone's thermal pools, the signs of volcanic energy take an unexpected form. Warm water rises through fractures in the crust, carrying dissolved minerals toward the surface, and within these heated channels, microorganisms have made a living where most familiar forms of life could not remain active. The volcanic system becomes a habitat shaped by heat, chemistry, and the constant movement of water. Thermophiles, microorganisms adapted to high temperatures, occupy some of the hottest environments. Certain species can remain active above 77 degrees Celsius or 170 degrees Fahrenheit, while others tolerate conditions approaching 100 degrees Celsius or 212 degrees Fahrenheit. Their cells contain proteins and membranes adapted to heat that would rapidly damage the biological machinery of ordinary organisms. For these microbes, temperature is not merely a limit, it helps define the boundaries of home. Their survival also shows how flexible life can become when generations remain exposed to unusual physical conditions, preserving traits that would seem impossible elsewhere. Grand Prismatic Spring offers a living map of this adaptation. Its brilliant blue center is surrounded by bands of yellow, orange, and brown, and those colors come largely from communities of microorganisms. Each group favors a particular range of temperature and chemistry, so the changing conditions from the center toward the cooler margins create a series of biological neighborhoods. What appears from a distance as a pattern of color is, at smaller scales, a shifting arrangement of microbial communities responding to the thermal gradient. One Yellowstone microorganism also changed the course of modern biology. In 1969, scientists studying a heat-tolerant bacterium called Thermus aquaticus discovered an enzyme that could withstand repeated heating. That enzyme made it possible to develop the polymerase chain reaction, a method that repeatedly copies selected portions of deoxyribonucleic acid. Because the enzyme remains functional after heating, researchers could cycle through the chemical steps needed for amplification without destroying the tool itself. The importance of that discovery reaches far beyond the hot spring where the organism lived. The polymerase chain reaction became fundamental to genetic research, forensic identification, paternity testing, medical diagnostics, and many forms of biological investigation. During the coronavirus disease 2019 pandemic, related laboratory methods became part of widespread testing. A microorganism from a Yellowstone spring had provided a molecular tool capable of working under conditions that resemble the heat of its original habitat, allowing laboratories to perform repeated cycles of heating without losing the enzyme's usefulness. Other thermal environments support archaeal microorganisms, including communities adapted to acidic springs, fumaroles, and boiling mud. Their unusual chemistry and metabolism offer researchers clues about how early life may have functioned when Earth's surface was chemically different from today. Some of these organisms obtain energy from minerals or gases instead of relying on the familiar food webs found in forests, rivers, and oceans. Much of Yellowstone's microscopic world remains difficult to catalog. Thermal features contain countless combinations of temperature, acidity, minerals, and gases, creating specialized habitats that can differ over very short distances. Many organisms living within those gradients have yet to be fully studied or formally described. The volcano, therefore, supports a biological story alongside its geological one. Heat that can reshape rock also creates conditions where specialized life can flourish, turning the boundaries of survival into places of adaptation and discovery. Across Yellowstone, an intricate web of instruments follows the volcano from ground level to the atmosphere. The system is designed to notice changes so small they would pass unnoticed in ordinary observation. Earthquakes, shifting ground, escaping gases, changing water chemistry, and subtle movements around the caldera are measured and recorded, creating a continuing portrait of a restless geological system. The Yellowstone Volcano Observatory brings together 9 institutions, including the United States Geological Survey, the University of Utah, the University of Wyoming, Montana State University, and state geological surveys. Their work forms one of the most coordinated volcanic monitoring efforts in North America. Seismographs listen for earthquakes as they happen. Global Positioning System receivers track changes in the shape of the ground with millimeter precision. Radar observations from satellites can reveal changes in surface elevation across the caldera, extending the view beyond individual instruments. Other measurements come from the chemistry of the landscape itself. Gas sensors watch emissions of carbon dioxide, sulfur dioxide, and hydrogen sulfide. Stream gauges follow changes in water temperature and chemistry within rivers connected to the hydrothermal system. Airborne surveys add another layer, with helicopters carrying magnetic and electromagnetic instruments that help reveal the electrical properties of fluids and rocks underground. Each method sees a different part of the same system, and together they create a much more detailed picture than any single measurement could provide. Every year, the observatory gathers these observations into a public report, allowing scientists to compare the latest measurements with the long record that came before them. Small variations can then be placed into context. An increase in earthquakes may belong to an ordinary swarm. A change in ground elevation may reflect the movement of hydrothermal fluids. A shift in gas emissions can have several possible causes. The value of continuous monitoring lies in seeing these changes as part of a pattern. That pattern matters because an approaching eruption would be expected to disturb several parts of the system at once. Earthquakes could become more frequent and intense. The ground could begin rising more rapidly. Gas emissions might change sharply, while hydrothermal areas could show unusual thermal or chemical behavior. Such signals would provide evidence that magma or volcanic fluids were moving toward the surface in a significant way. At present, the network has not observed that combination of warning signs. Recent earthquake activity has remained within the range expected from Yellowstone's background behavior, and the larger changes associated with an impending eruption are absent. In 2024, monitoring recorded 1,173 located earthquakes below the typical annual range of 1,500 to 2,500. The largest reached magnitude 3.3 in January and belonged to a swarm of 112 earthquakes. These numbers do not mean the volcano is inactive. Yellowstone continues to breathe through earthquakes, hydrothermal circulation, and shifting underground fluids. What they show is more specific. The system is being watched closely, and the measurements do not currently resemble the pattern expected before an eruption. For a volcano capable of events separated by hundreds of thousands of years, that distinction matters. The instruments are not waiting for a dramatic moment. They are searching for small changes that, when gathered together, would form a recognizable signal. A volcano approaching eruption would begin changing long before the surface revealed anything dramatic. Deep underground, magma moving through fractured rock would disturb the crust, alter pressure, release gases, and transfer heat into surrounding fluids. Each change would leave traces that instruments could detect, allowing scientists to follow the progression as separate signals gradually became part of a larger pattern. Earthquakes would be among the earliest clues. As magma pushes through solid rock, it creates fractures and shifts existing faults, producing changes in earthquake frequency, location, and depth. Ground elevation could also begin to change as pressure builds within the volcanic system. Global positioning system instruments can measure movements as small as millimeters, while satellite radar can map deformation across broad areas. A meaningful acceleration in these signals would stand out from Yellowstone's ordinary fluctuations. Chemistry would add another layer of evidence. Magma contains dissolved gases, including carbon dioxide and sulfur dioxide, that can escape as molten rock rises. Increasing emissions, especially when combined with seismic changes and ground deformation, could indicate that deeper processes were moving toward the surface. Hydrothermal features might respond as well, with shifts in temperature, acidity, water chemistry, or flow revealing changes in the underground pathways carrying heat and fluids. This is why the idea of Yellowstone suddenly detonating without warning does not fit the behavior expected from a large volcanic system. A supereruption requires enormous quantities of magma and pressure to interact with the surrounding crust. The physical changes involved would create many opportunities for detection. The instruments across Yellowstone are designed to notice those changes while they are still developing. A study published in 2017 by researchers at Arizona State University brought a different detail into the discussion. By examining minerals preserved in ash from the eruption approximately 631,000 years ago, researchers suggested that parts of the magma system may have moved from a long-lived state toward eruption readiness faster than earlier models had assumed. The possibility of a transition occurring over decades rather than centuries attracted considerable attention. The ancient minerals, however, recorded the conditions surrounding that prehistoric eruption. They did not show that the same transition was occurring in Yellowstone today. The study also emphasized the need for additional research before drawing firm conclusions about how quickly a future eruption could develop. The distinction matters because evidence about what happened in the past is different from evidence showing what is happening beneath the volcano now. Current observations provide no indication of the escalating pattern that would be expected before an eruption. Earthquake activity remains within the range of background behavior. Ground deformation has not entered a sustained phase of rapid uplift. Gas emissions and hydrothermal conditions show fluctuations, yet they do not display the coordinated changes associated with major volcanic escalation. Michael Poland, a scientist who has studied Yellowstone extensively, has expressed strong confidence that an approaching eruption would produce detectable warning signs years in advance, potentially even decades. That confidence comes from the number of independent measurements available and the length of time scientists have been observing the system. The monitoring network, therefore, serves a purpose larger than watching for catastrophe. It creates a record detailed enough to distinguish ordinary volcanic behavior from genuine escalation. At Yellowstone, reassurance comes from evidence gathered day after day, measurement after measurement, with the landscape itself providing the signals that scientists are trained to recognize. A volcano can outlive the people who study it, yet its lifetime still has a beginning, a middle, and an eventual decline. For Yellowstone, that decline may already be written into the chemistry of its magma. Volcanologists have spent generations learning how eruptions begin, how magma rises, and how pressure accumulates. Volcanic aging remains a younger field. Understanding how a supervolcano loses the ability to erupt may be as important as understanding how it became capable of doing so. Inside a large volcanic system, heat is the currency that keeps magma mobile. Fresh heat entering from deeper parts of Earth can preserve pockets of melt within a much larger body of crystallized rock. When that heat supply weakens, crystals begin forming throughout the remaining melt. The magma becomes crowded with solid minerals until the mixture resembles a sponge of crystals with smaller amounts of melt threaded through it. Eventually, the proportion of liquid can fall below the level required for an eruption. This transformation does not need a dramatic final moment. Each period of cooling can leave behind more crystallized material while the remaining melt becomes isolated into smaller pockets. After an eruption removes part of the system, the reservoir also loses heat through the surrounding crust. Repeated cycles shift the balance towards solid rock. Yellowstone's three major supereruptions each removed enormous volumes of magma-rich material, adding another part of the long geological story of cooling and reconstruction. The older volcanic fields along the Snake River Plain offer a distant comparison. They were produced by the same moving hotspot that eventually fed Yellowstone, yet their volcanic systems have passed into a different stage. Their former heat sources are now expressed mainly through solidified rocks, basalt flows, and layers of sediment. There are no active calderas producing the hydrothermal energy seen at Yellowstone or continuing volcanic unrest comparable to the modern system. That contrast gives scientists a rare opportunity to study volcanic life as a sequence rather than a single event. The older fields show what remains after a volcanic province has exhausted the conditions that once sustained repeated eruptions. Yellowstone provides the younger chapter, where heat still moves through rock and water, and where magma remains present at depth. The distinction matters because extinction does not necessarily arrive as a final eruption. A supervolcano can gradually lose its eruptible character as crystals accumulate and accessible melt diminishes. From the surface, this process may unfold across intervals longer than human history. A landscape can continue producing hot springs and steaming ground while the deeper magma system becomes progressively less capable of assembling the conditions required for another enormous eruption. Yellowstone is therefore neither a volcano that has simply switched off, nor a system whose future can be reduced to a single prediction. Its thermal activity shows that substantial energy remains within the crust, while its geological ancestry records volcanic systems that eventually ceased to erupt. Determining where Yellowstone sits along that continuum requires studying magma chemistry, crystal growth, heat flow, earthquakes, ground deformation, and hydrothermal behavior together. The deeper lesson is that volcanic death may be less like an ending and more like a long change of state. Heat fades, crystals accumulate, and the architecture that once carried magma toward the surface becomes increasingly solid. In geological time, even a system capable of reshaping continents can gradually become part of the rock around it. A line drawn across a map of the western United States would seem almost motionless, yet the crust beneath Yellowstone is traveling every year. The North American plate moves southwestward at roughly 2.5 centimeters, which is about 1 inch each year. That movement is too gradual to notice during a human lifetime, though geological time turns such small distances into journeys measured across entire regions. The source of Yellowstone's volcanism is commonly described as a hotspot, a persistent region of unusually warm mantle beneath the moving plate. The surface does not remain fixed above it. As the plate drifts, the crust passes over the deeper heat source, leaving a trail of volcanic centers across what is now the Snake River Plain. Yellowstone occupies the youngest part of that trail, while older volcanic fields record earlier positions of the plate. That relationship gives the landscape a kind of geological clock. The plate continues its southwestward motion, carrying Yellowstone away from the position where the hotspot first influenced this part of the continent. The underlying mantle source can remain active while the surface expression migrates. Across a million years, the distance covered by the plate would be roughly 25 kilometers, which is about 16 miles, enough to place the volcanic system in a noticeably different crustal setting. One of the most important changes lies ahead in the Beartooth Plateau. This region contains exceptionally old and thick continental crust formed from rocks that have endured immense spans of geological history. Thick continental crust presents a more difficult route for magma. Heat rising from the mantle must travel farther through solid rock, and melting conditions become more complicated as the crustal architecture changes. That makes the distant future difficult to predict with confidence. Scientists have no controlled example of a Yellowstone-like hotspot passing beneath crust of this exact character. The geological record offers clues, yet it does not provide a complete script. The plume could gradually lose its ability to generate eruptible magma as the crust becomes a less favorable pathway. Hydrothermal activity could then diminish as the deeper heat supply weakens, leaving springs and other thermal features to cool across hundreds of thousands of years. Another possibility is more complicated. Heat could accumulate beneath the thick crust for a very long interval, allowing new pockets of melt to develop before any pathway toward the surface becomes available. Such an event would arise from conditions unlike those that shaped Yellowstone's earlier volcanic centers. The timing, scale, and even the eventual style of volcanism cannot be established from present observations alone. For the people living around Yellowstone today, this geological clock moves almost beyond the meaning of ordinary time. A million years contains more generations than any civilization can count, and the landscape itself would be transformed many times before the plate carried the region into its next setting. Rivers would change course, mountains would erode, climates would shift, and new ecosystems would replace old ones. The remarkable part is the patience of the process. A movement measured in centimeters each year can gradually guide the fate of a volcanic system across millions of years. Yellowstone's future is therefore written partly in motion so gradual that a single human life cannot perceive it, while the Earth records every fraction of that journey. The landscape of southern Idaho carries a long volcanic trail stretching southwest from Yellowstone across the Snake River Plain. For roughly 1,207 kilometers, which is about 750 miles, the surface records the passage of a hotspot across the continent. The distance is immense on a human map, yet it represents only one portion of a much longer journey written into the crust. Each segment preserves a different stage of the same moving volcanic story. Much of the plain is covered by basalt, yet beneath those dark flows are the remains of volcanic centers that once dominated this region. The trail began forming about 17 million years ago as the North American plate moved across the underlying mantle hotspot. Volcanic centers appeared, grew, erupted, and gradually shifted with the moving crust. Some developed enormous magma systems capable of producing caldera forming eruptions. After those systems cooled, later basaltic lava spread across the landscape, covering portions of the older structures and softening their outlines in the geological record. Dozens of calderas are associated with this volcanic province, although many are difficult to recognize from the surface. Their buried remains preserve a sequence of changing volcanic centers, each belonging to a different position along the path of the moving plate. What appears today as a broad plain, therefore, contains a much more complicated history, layered one volcanic episode over another. The Heisey volcanic field provides a particularly useful chapter in that history. Its final caldera forming eruption occurred about 4.45 million years ago. Afterward, the region entered a long interval without another comparable eruption. Roughly 2.3 million years passed before the volcanic focus shifted toward the Yellowstone region. Heise is now regarded as extinct, its former activity preserved mainly in rocks and deposits scattered through the landscape. Farther southwest lies the Picabo volcanic field, followed still earlier by the Bruno Jarbidge Volcanic Center. Their histories follow a broad pattern. Large eruptions marked periods of intense activity, followed by smaller volcanic episodes and longer intervals of decline. Eventually, the heat and magma pathways that sustained those systems faded from the surface record. Seen together, these volcanic fields create something like a geological procession. Each center occupied the landscape for a time, expressed its stored heat through eruptions and hydrothermal activity, and then yielded its place as the plate continued moving. Their former calderas became increasingly difficult to distinguish as lava, sediment, erosion, and later geological changes reshaped the terrain. Millions of years from now, Yellowstone could become another chapter in that same procession. Its hydrothermal features would eventually cool if the deeper heat supply diminished, while erosion and new sediment gradually altered the land above the former volcanic system. The geysers and hot springs would belong to a vanished phase of the landscape, replaced by ordinary rock and changing ecosystems. Older rocks remain as witnesses under newer landscapes. The Snake River Plain therefore offers a rare kind of perspective. It shows that a volcanic system can dominate a region for a geological moment and then become part of the landscape it once transformed. Yellowstone is the youngest major expression along this trail, still active today, while the older centers remain as records of what happens when a hotspot moves on and a volcanic chapter reaches its natural end. The story of Yellowstone can be imagined without a final explosion. Its ending, if the volcanic system continues along a declining path, may arrive through a gradual reduction of heat, pressure, and movement, spread across spans of time so long that human history becomes only a small mark within them. For generations, the public image of Yellowstone has been shaped by catastrophe. Films, headlines, and speculative countdowns have turned the caldera into a symbol of sudden destruction. Geology offers a different rhythm. Volcanic systems can lose their ability to produce major eruptions through cooling and crystallization, while the surface continues to change in much less dramatic ways. A landscape built by immense forces can eventually become ordinary again. The first signs of such an ending would unfold through the hydrothermal features. Geysers depend on carefully balanced channels, heat, water, and pressure underground. As the deeper heat source weakens, eruptions could become less frequent or less vigorous. Old Faithful already varies naturally in its intervals, influenced by the amount of water entering its plumbing and by other local conditions, so changes today cannot be treated as proof of long-term decline. Far deeper in geological time, however, a cooling system could eventually leave its geysers without enough energy to erupt. Steamboat Geyser would belong to that same transformation. Its spectacular eruptions could become increasingly uncommon as the conditions feeding them changed. Hot springs would also respond. Their temperatures and chemistry would shift, altering the microbial communities that create their familiar colors. Thermophiles adapted to hotter water could retreat toward remaining warm areas, while cooler communities expanded into spaces they once could not occupy. The caldera itself would carry another record of decline. Today, its floor rises and falls as fluids move through fractures and pressure changes beneath the surface. With progressive cooling, those cycles could diminish as the deeper system loses heat and circulating fluids become less abundant. Earthquake swarms associated with hydrothermal movement could also become less common. Fractures would gradually seal as minerals crystallized from cooling fluids, reducing the pathways through which water and pressure travel. What would remain is not an empty landscape, but a geological archive. The caldera spans roughly 48 by 72 kilometers, which is about 30 by 45 miles. Its rocks preserve the traces of around 80 lava flows, while the plateau contains the chemical and structural evidence of roughly 10,000 hydrothermal features. Geysers and springs may fade, yet their former pathways can remain recorded in minerals, altered rock, and subtle changes in the ground. Such an ending would have no single date. There would be no final hour announced across the world, no dramatic boundary separating activity from extinction. The transformation would unfold through countless small adjustments, each almost invisible within a human lifetime, while forests, rivers, animals, and weather continued their own cycles across the changing ground, year after year. Heat would diminish, fluids would slow, fractures would seal, and the landscape would continue beneath changing skies. A system capable of shaping an enormous region can therefore reach its final state through patience rather than spectacle. Yellowstone may one day become another extinct volcanic center, its former energy preserved in stone, its hydrothermal waters replaced by ordinary groundwater, and its great caldera left as a lasting shape upon the continent. There is another way to look at Yellowstone, one that begins far below the familiar geysers and springs. The heat rising through this landscape belongs to a planetary process that has been unfolding for millions of years, moving energy from Earth's deep interior toward the surface. The volcano is one expression of that exchange, and its eruptions are only brief moments within a much longer geological rhythm. For roughly 17 million years, the mantle plume beneath this region has helped reshape the continent above it. As the North American plate moved across the hotspot, volcanic centers appeared, grew active, and were eventually carried away from the source of heat. Their remains became part of the Snake River Plain. Lava altered the landscape, weathering created mineral-rich ground, and rivers gradually worked those materials into new soils. The same geological machinery also sustained the hydrothermal environments that became laboratories for studying life under extreme conditions. One discovery from those waters reached far beyond Yellowstone. A heat-tolerant microorganism provided an enzyme capable of functioning at temperatures that destroy many biological molecules. That enzyme became essential to polymerase chain reaction, a technique that transformed molecular biology, medical research, forensic investigation, and the study of inherited traits. A volcanic landscape that can preserve evidence of immense eruptions also helped provide a biological tool for reading the microscopic instructions inside living cells. The connection between creation and destruction runs deeper still. The heat associated with the Yellowstone hotspot has produced enormous eruptions, yet it also feeds the geysers and springs that draw millions of visitors each year. Energy from the same deep source can fracture rock, melt crust, circulate groundwater, nourish unusual ecosystems, and build new volcanic terrain. The Earth does not separate these outcomes into neat categories. They belong to one continuous system. That perspective changes the scale of the story. Human history is measured in generations and centuries, while Yellowstone's geological history unfolds across millions of years. A landscape can appear stable during an entire lifetime, while its deeper structure continues to evolve. Magma crystallizes, faults shift, groundwater circulates, and heat migrates through rock, all within processes whose full movements may require spans of time far beyond direct human observation. The record preserved around Yellowstone has also given scientists a rare archive of changing climates, volcanic activity, and ancient environments. Ash layers can help place fossils and sediments within a broader chronology, allowing separate discoveries across the continent to be connected through time. What once existed as scattered fragments becomes a sequence, written into rock and read across generations of scientific work. Yellowstone has therefore become more than a place associated with enormous eruptions. It is a natural laboratory for understanding mantle plumes, partially molten volcanic systems, hydrothermal ecosystems, and the ways planetary heat can shape a surface inhabited by life. Each measurement adds another piece to that larger picture. The deeper lesson is not that the Earth is safe or dangerous, it is that the Earth is active. Its interior continues to release energy, reshape landscapes, and influence life without following the scale of human expectation. We live on its surface while another world moves beneath our feet, governed by processes that began long before us and will continue long after us. Understanding that movement turns Yellowstone from a symbol of catastrophe into something more enduring, a window into how a living planet manages its own immense supply of heat. 2,100,000 years ago, the landscape we now call Yellowstone belonged to a different world. There was no national park, no familiar forest, and no human presence to give the place a name. Deep beneath the surface, molten rock gathered until the ground could no longer contain the pressure. The eruption transformed the region into a field of ash and volcanic debris, leaving behind a caldera roughly 97 kilometers wide, which is about 60 miles. Afterward, The landscape began the patient work of recovery. Plants returned first, followed by animals, soil, rivers, and forests. What had been transformed by heat became a place where life could establish itself again. Then, about 1,300,000 years ago, another enormous eruption reshaped a different part of the region. The same broad volcanic system produced another caldera, another period of devastation, and another gradual return of living things. Geological time allowed the landscape to recover without haste. Around 631,000 years ago, the third great eruption created the caldera that dominates Yellowstone today. Its collapse altered the shape of the region, while later lava flows gradually occupied portions of the depression. Ice eventually crossed the landscape, carving and polishing the ground. When the glaciers retreated, forests expanded across the recovering terrain. Large mammals followed. Much later, human beings arrived, carrying fire, tools, stories, and eventually cameras. Today, the evidence of that immense history appears in forms that seem almost delicate. Steam rises from Grand Prismatic Spring. Old Faithful sends heated water into the air. Pools shimmer with colors created by microorganisms adapted to conditions that would exclude most other forms of life. These features are the surface expression of heat moving through rock and groundwater, a process connected to a volcanic system that has influenced this region for roughly 17 million years. The landscape, therefore, carries several ages at once. A geyser may complete its cycle within minutes, while the rock beneath it records events separated by hundreds of thousands of years. A forest can grow and disappear within a few centuries, while the volcanic structures supporting its soil remain for millions of years. Human generations occupy an even smaller interval, leaving trails, photographs, buildings, measurements, and memories that eventually become part of the geological record themselves. Far ahead, the movement of the North American plate will continue. The hotspot will remain deep below the continent while the surface travels across it, carrying Yellowstone toward a geological setting different from the one that shaped its present form. Whether that change eventually brings greater cooling, renewed activity, or some process not yet understood belongs to a future measured in millions of years. By then, every person alive today will be part of the distant past. Institutions will have changed, languages will have changed, and the questions asked by scientists will belong to another age. Yellowstone itself will continue to be altered by erosion, ice, rivers, volcanic heat, and the movement of the continent. For now, the ground remains warm, the geysers still rise, and life continues across the caldera. The landscape does not need to hurry. Its story has always been written on a scale larger than a human lifetime, and the next chapter will unfold according to the patient movement of Earth itself.